To understand the function of a turbine blade, we must first understand how a jet engine works. The aim of a jet engine is to eject air at high speed. According to Newton's third law, this will produce an equal and opposite force of thrust, which pushes the aircraft forward. First, air is drawn into the engine via fan blades. This air is then forced through the compression stages, where it is squeezed to 1/20th of its original volume and to over 600 degrees Celsius in temperature. This high pressure and high temperature air is mixed with fuel and ignited. Now 1700 degrees Celsius, the mixture expands rapidly and creates a ferocious jet of high velocity gas. The turbine blades aim to harness this energy. In a similar fashion to wind turbines, the turbine blades are forced to rotate around a central engine shaft. This powers the fan and compressor stages, allowing more air to be drawn in, and therefore continuing the cycle. Every blade extracts the same power as that of an F1 car engine. Every blade experiences a centrifugal force equivalent to the weight of a double-decker bus. The blades rotate at 1.5 times the speed of sound. In addition, the blades are required to operate at 1700 degrees Celsius. It is vital that turbine blades can withstand these high temperatures and large stresses. The only material capable of this is a single crystal superalloy. A superalloy is defined as a high-performance alloy with the ability to operate at a high fraction of its melting point. A single crystal alloy eliminates the presence of grain boundaries and associated weaknesses at high temperatures. We use a nickel-based superalloy consisting of a two-phase microstructure, the gamma and the gamma prime phase. The gamma phase is a disordered structure due to the addition of a small amount of aluminium to a nickel lattice. In regions of greater aluminium density, gamma prime precipitates form. The gamma prime phase has an intermetallic structure because it becomes more favourable for the aluminium to arrange themselves in an ordered fashion. The change between the disordered gamma phase matrix to the ordered gamma prime precipitates produces the mobility of dislocations. This in turn increases the material's resistance to fracture. In practice, the turbine blade superalloy consists of more elements than just the base nickel and aluminium. Elements are carefully chosen for their individual properties. Rhenium, for example, provides increased creep resistance. Overall, the single crystal superalloy has been carefully crafted from the atom up, allowing it to experience large forces and extreme temperatures. Unfortunately, our superalloy is still operating in an environment 500 degrees Celsius above its melting point. In its current standing, it's going to melt. To increase the temperature capability of the superalloy, we first need to add a thermal barrier coating. This coating acts as an insulator to keep the material cool. It also provides corrosion and oxidation resistance. Thermal barrier coating consists of 3 layers. The first layer is an aluminium-based bond coat that joins the thermal barrier coating to the superalloy. It also acts as a barrier to prevent atoms diffusing out of the superalloy. Second is a thermally grown oxide layer, which is formed by oxidizing the aluminium found on the bond coat surface. This prevents further oxidation beneath the coating and reduces the chance of crack formation and erosion. The third layer is a thermally insulating ceramic top coat. It is a low thermal conductivity ceramic with good high temperature stability. It is this layer which provides the insulation. A 200 micrometer coating can reduce a superalloy surface temperature by up to 200 degrees Celsius. The second method is to cool the superalloy. Cool air, albeit at 600 degrees Celsius, is taken from the compressor and passed into the root of the turbine blade, and through a series of intricate internal channels. Channels are serpent-like and wind through the blade to maximize contact surface area. This allows for lots of thermal energy to transfer from the high-temperature superalloy to the cooler air. In addition, when the high-pressure cooling air escapes the blade through the holes on its surface, it creates a thin insulating film of cool boundary air. This in turn reduces the heat transfer from the main gas stream. These two methods manage to keep the blade's temperature down to 1100 degrees Celsius, just below its melting point. Jet engine turbine blades have been engineered to operate at a staggering 500 degrees Celsius above their melting point, not unlike trying to keep an ice cube frozen in an oven. Currently, scientists are working to increase the temperature capability of turbine blade superalloys even further. Higher turbine temperatures result in better engine efficiency and less fuel usage. Aviation causes 2% of global carbon emissions, and it is vital that we continue to find ways to make alloys even hotter.